Hi, what is up? It's the new me. So I'm trying out different workflows to make things easier for myself. So let me know if you like this one better or however I used to do before. So anyways, oh, by the way, this video is completely unscripted, so I have no idea how this will turn out by the end. Go easy on me on this one. Anyways, okay, so we've cleared the vertical asymptotes. So as a natural progression, we move on to the horizontal asymptotes. Although, I'd like to point out one thing before. If you look at your book, you'll notice that there's a third type of asymptote called an oblique asymptote. And this is where I'd like to take a bit of liberty, where I would like to call the vertical asymptotes as the X-asymptotes, and the horizontal and also the oblique asymptotes as the Y-asymptotes. You'll know about this soon enough. So what if the power of the numerator is 1 more than the denominator? I'll tell you what. For example, let's say we have x squared plus 2x minus 1 divided by x minus 1. How would we attempt to turn this into a proper fraction? Well, of course, there is a shorter way, but you kind of need to have a bit more understanding of how fractions work in terms of functions. So let's leave that aside for now. So if we apply the long division, what we end up with is this. So this would turn into 2 by x minus 1 plus x plus 3. So this is clearly different from the previous form, which was, the only difference is this d over here. It's no longer a constant, but a function. And now if you remember how our horizontal asymptotes work, this thing was simply y equals d. So if you apply that logic here as well, then our quote horizontal asymptote would turn into y equals x plus 3. But of course, if you look at it a bit deeper, this is not really a constant. In fact, this entire thing is just a straight line like this, which means what we learned before as the horizontal asymptote is actually a diagonal asymptote, or in this case, an oblique asymptote. And this is exactly why I prefer to call them the X-asymptote and the Y-asymptote. Because the vertical asymptote stays the vertical asymptote, but whatever is outside the proper rational function turns out to be the value of y, like the entire thing. So with that out of the way, we can sketch this function. Here, we have x equals 1 would be here. We have our vertical asymptote. And over here we have 1, 2, 3. What is y equals x plus 3? It is, of course, this line over here. So these are our two asymptotes. In this kind of situation, you actually end up with two types of rational functions. You either end up with a function like this, or you could end up with a rational function like this where it flips around. So how do you even figure out which one it is? Which pair of rational function is it? The answer to that is, of course, differentiation. Because if you look at these curves, only the blue curve has turning points. So if you find turning points, then you'll automatically know that the sketch should be the blue function. But if you don't find any turning points, then you can automatically safely assume that it's your red function. Let's try this out. We have y equals this as our function, as our main function. If we try to differentiate this, we end up with, okay, so these are our two roots. So turns out these, in fact, are our stationary values, which means that our actual graph, we have this, we also have this, an oblique asymptote. So right here, we have 3, we have 1, we have 1 plus square root of 2, we have 1 minus square root of 2. And this is what the graph actually looks like. You can test this out in your graphing software. Let's try out another sum in a more systematic manner, all right? Okay, so let's say we have the function x squared minus 4 divided by x minus 1. So at first, we need to write this in a proper rational function. So let's try dividing this. We have x minus 1, and here x squared minus 4. This turns out to be minus 3 divided by x minus 1 plus x plus 1. If we are to differentiate this, then we end up with 3x minus 1, 2 plus 1. Equate this to 0. We have, which means x minus 1 is plus minus square root of minus 3. And I think you can realize there is no real stationary points. So now, if we are to sketch the graph, we have our asymptotes. The x-asymptote is x equals 1, and the y-asymptote is x plus 1. We have 1 over here, we have 1 over there. Draw the vertical asymptote, draw the oblique asymptote, and since there are no stationary points, it means that the graph is actually like this. Feel free to test it out in your graphing software as well. So this would be your basic sketch, but we can make this a bit more accurate by writing down the intercepts. So your x-intercept would be when y equals 0. If y equals 0, that means x squared minus 4 is equals to 0 as well. And then x is plus minus 2, which means that this is 2 and this is minus 2. Then for the y-intercept, we have x equals 0, which means y equals minus 4 divided by minus 1, or in other words, just 4, which means this is supposed to be 4. So technically speaking, there should be a bit more of a gap in my sketch. But it's no big deal. As far as you're concerned, find out these values beforehand. So what we have is just 3 check marks. The first is find the asymptotes, find the intercepts, and find the stationary points. As long as you have these 3 things, all's good. So yeah, hopefully my scuffed rigging didn't bother you too much and the lesson was actually helpful. As far as this video is concerned, as long as you remember these 3 points, you should be able to handle any kind of rational function that comes your way, including what we'll handle in the next video, where you have to deal with more than 2 line asymptotes. That also means that we'll be finally getting into the continuity thing I talked about in the first video. And so yeah, thanks for watching, and I'll see you in the next one. Take care.